first questions I received was follow-up questions on TAT 4.2. So TAT 4.2, let's just set the scene again. We've got these reactors in series with our heat exchanger there. And there we go. Cool. Okay. And some of the questions specifically relates to what do I do if I have a packed bed reactor. On this diagram of ours, there we go, X temperature, what do I do if I have a packed bed reactor? So I will get to that in a bit. I just want to make use somebody who asked me some questions. I want to use what we discovered from their code as a warning. Remember, this whole figure, X, relates to a specific inlet molar flow rate state divided by Q. And then you multiply this by 1 minus X to get a concentration. So this is actually a concentration versus temperature figure. So X is just another way of representing a change in concentration. And if I now want to calculate something on this diagram and relate it to an X value, this must be related to this inlet molar flow rate, okay? And then I know some of you you like to, when you consider the second reactor, like to use an incremental conversion. So let's call that X2 star. So I can either have X2 star or I can have X2, the overall conversion. If I calculate the concentration here, a frequently made mistakes, and I've made this mistake myself just, by being in a rush or being stressed, is if I want to calculate the concentration of A and the concentration of B in the second reactor. If you use the purple line for calculating your concentrations, it can be Fa0 times 1 minus X2 divided by the Q. That's now for our liquid phase reaction. And this can simply be equal to Fa0 times X2. Happy. Then I will have the concentration there because I've calculated the flow rates over there based on my inlet condition. However, if I want to use the incremental value, so let me just use red to indicate that. So if I want to use that, I need Fa1 over there. And the temptation then is to use just a similar equation set and to say my concentration of A, that one, is equal to Fa1 times 1 minus X2 star divided by Q. And my concentration of B is equal to Fa1 times X2 star divided by Q. And this is wrong. And the reason why it is wrong is that Fb1 is not naught. So the molar flow rate of 1 that you must use there is equal to Fa1, whatever is formed, that is correct. That's the amount that is formed in that reactor, plus Fb1. And of course, Fb1 I can write in terms of Fa0 times 1 minus X over reactor 1. Please be careful. When you calculate, use the incremental approach to make sure that when you calculate the Fb coming out of here, that you use to calculate the concentration of B, that it is correct. Remember, it's the concentration in here that you want. It depends on what is the molar flow rate there. So careful, it's an easy mistake to make. Any questions on that? You've been warned. Questions? Hands up? No hands. Okay, so clearing, and let's now talk about packed bed reactors. So we haven't explored the packed bed reactor. I asked you that 4.2c. But I said, all right, if you now have this figure and you have your energy balance with your given inlet conditions, and then in both 4.1 and 4.2, we explored the fact that regardless of whether I have a CSTR or a PFR reactor, if I have adiabatic conditions, that is going to be the maximum conversion. Even if my del Cp is not equal to 0, right? We can approximate that line. We explored that in one of our previous stats. We may just ignore it for the sake of, first trial and say, okay, that is the limiting case. So therefore, for a PFR and a CSTR, that energy balance will follow exactly the same path. For a CSTR, you will jump, so let me just get a color for my CSTR. For the CSTR, you will jump to a specific X and temperature, and you have one reactor that operates at that state. For a plug flow reactor, different color. Let's take colors. I'm limited in colors. Let's take black. There we go. Plug flow reactor. What's going to happen as I enter there, I'm going to gradually climb up this little adiabatic slope. This is the path that the temperature, the X, and everything will follow in my adiabatic PFR. So if I'm there, I'm going to have this rate. If I now want to look at my ISO rate line, so I've got my ISO rate lines. This is going to be the rate over there. If I'm a little bit further, that's going to be the rate. If I'm a little bit further, that's going to be the rate. So I'm not going to have a rate at which my reactor operates like the CSTR. I'm going to have this changing rate. So on the Levenspiel plot, once again, on the Levenspiel plot versus X, it may look like that. So for the PFR, I am going to follow that rate, and therefore that area that's below the line times FA naught will give me the total volume of my PBR, or the PFR, sorry, volume. So the question, some people ask the question, is the energy balance the same? Yes, it is the same, but because I don't jump to a certain point when I operate, like in my CSTR reactor, there's the sudden jump, I gradually climb up this hill. One of the advantages of this in a PFR is that I will never have the issue of multiplicity. It's not possible to exist here, right? So how do I model this? And then people ask me about series reactors. If I now want series reactors, PFR reactors. So I have PFR1 and then intercooling and then PFR2. That is actually, yes, you can model it, and I will show you how to model it. But the advantage of having this intercooling thing that we have with the CSTR reactors, and that's why you will not do this for a PFR reactor, is the fact that I can adiabatically determine where is the maximum in the rate, operate there, cool, go to a maximum in a rate, cool, and operate that reactor at that maximum in the rate. And now what we must realize for the PFR, that doesn't exist. I do not operate at a maximum rate. I operate at lots of rates inside my PBR or my PFR as I follow. So when you model this, I would actually challenge you to model that 4.2C. So for that 4.2C, make your reactor volume really large. So take a volume like 5 times your biggest CSTR volume that you calculated. This is good practice. So practice this for your, almost I want to say, exam. And then we are going to have our normal solve IVP or ODE or whatever you, solve IVP if you want to use events. Procedure, and you're going to have to define your function and define your PFR, and you're going to have your independent variable and your variables. And your variables, it will then be FA, FB, and the temperature. And you're going to have your differential equations for each of them. This one is still just going to be, these two are just going to be equal to the rates. So the FA is simply going to be equal to RA. And the FB is going to be equal to RB, which you can relate, that is equal to min RA. And in order to populate each of them, I have to calculate a concentration. Concentration of A is going to be my FA divided by Q. Concentration of B, CB is FB divided by Q. And for the temperature, I now just need either, if you want it as a variable that you want ODE or solve IVP to integrate over, you are not going to supply that algebraic equation for your line. Then you must give this the TdV equation, and that is, of course, going to be equal to RA del H reaction divided by sum Cp or times Fa at the naught inlet conditions for each of the components. So either that, or you are not going to have this as a variable there, but then you have to, for each Fa, you are going to have to calculate that temperature using temperature is equal to T naught minus epsilon del H reaction divided by sum of that carrying capacities. I'm really sorry that I write over everything because my lack of spatial planning. Yeah, I will get better at this. Maybe if you come back in 20 years, I would have sorted this out. Okay, so this is either the algebraic equation that you're going to use, and the epsilon you then will have to write in terms of your Fa that you have calculated there. But then if you are now at the outlet, so this is there, and now you have an outlet for that PFR. So first thing I want you to do is to solve for a very large volume. So no events, just see what happens to the profile. So if you have a very large volume, if I have a very large volume and I want to evaluate how X, now for X I'm going to calculate this after my integration procedure. I can calculate my X and I want to plot it along the volume. It's going to do this. It's going to start at a low rate. The rate is going to increase until that maximum value where you're going to operate your CFR, but the PFR goes past that point. The rate starts to decrease, and then it's going to look exactly like those profiles you were drawing for that 4.1 when I asked you to draw that profile. And this is that maximum conversion where it is going to stop. So this line xt should correspond, if you did everything correctly, to whatever you calculated there by solving simultaneously for your adiabatic energy balance and your X equilibrium line. So for a very large volume, this is just what you are going to get. So if you want to, now let's say you go to that maximum that you can find. I go to that maximum that I can find, and now I cool it down. So our carrying change. Okay, let me just, the carrying capacity go into the second reactor, it include the inert and the nulliform P. Okay, let's talk about the carrying capacity, but let's say I now size it to say, okay, up till equilibrium. So just until it reaches equilibrium, it's going to be a fairly large reactor. Then of course, if I cool it down and equilibrium, I can start again with that PB or the next PBR reactor, because now I've changed the inlet temperature, so I can spec a new inlet temperature there. But the question that I asked in terms of minimize the volumes, that doesn't exist anymore, because you can't operate at a maximum rate. You will just, for the second reactor, you will see the same kind of behavior. You will have an X and it will go until you achieve equilibrium. Important that T02 that you will have to calculate FA02 and FB02, similarly to what you've done with the CSTR reactors. So this is going to be equal to FA01 minus X1 and FA0 X1. So you will have to calculate a new set of inlet variables. Sure, you can specify that. And then you can indeed, if you want to, play around with this T0 to see where is an but you need much more information, or you need to make clearer to yourself, how am I going to play around with trying to optimize the volumes here? I am not going to expect that of you, those who ask the question. So I am definitely not going to change this question to say optimize volumes of two PFRs in series, because you simply will not build the PFRs like that. The PFRs, and that was what we're going to explore after the semester test, much better to have a single PFR, non-adiabatic, so that you can, that that jump in temperature that you want to achieve in a CSTR. There you want jumps. Jumping temperature, boom, to the maximum. Jumping temperature, boom, to the maximum. Because you don't have that. You have this gradual temperature profile. You can play around with that variable, the stuff that affects that, the A value, which in other words is directly proportional to the diameter of your tubes. You can play around with that value to affect that. You can play around with your utility temperature. In order to have a non-constant temperature here, manipulate the temperature as you are going along the line in your backbed reactor. You will be able to pass that adiabatic conversion there, equilibrium. You will be able to surpass it to a very great extent if you do that, and even achieve 90% to 80% conversion by constantly cooling. And then it becomes quite hairy to visualize it on this figure here, but we are going to have a lab session touch where I will show you how to play around with the variables in order to optimize then for this volume. But that optimization becomes a design exercise, and each student will find a different answer depending on what he varied. So that's a very difficult question to ask in a test because it's very open-ended. For plug flow reactors, it's an open-ended question. Manipulate. So what Josh is asking, and often because I want a very specific temperature profile, and you can in fact say, all right, I introduce, but that becomes a heat exchanger design problem, is to say I introduce a utility at different points along the length of my PBR, or I have co-current flow, or I have counter current flow, and that of course will affect the energy balance. So yes, certainly you can explore that. We will not do that in this course, but you can explore that possibility when you are designing your reactors and you have this kind of reactor that you have to size, of course, next semester. So you can. Right, so let's just talk about this energy carrying capacity. Does the energy carrying capacity change along the length of your PBR? Pencil. Along your PBR, because you have an FI naught, and you have, what happens is you have FA, FB, and temperature, and you've got this inert. So the inert flow rate stays exactly the same. Your FA is going to decrease. There, you're going to have a decrease. FB, you're going to see an increase. So this is FB, this is FA. But if the del Cp of the reaction is equal to 0, you've got two options of calculating that energy carrying capacity, and by that I now mean this term, Fi Cpi. If del Cp reaction is equal to 0, and we work with average Cp value, so the fact that the temperature is increasing, I am not taking that into consideration when I calculate my Cp value. So I use the Cp values at the inlet, and that is actually relatively fine for most applications when there's not a huge increase in temperature. So I can calculate that by saying I am going to take the flow rates as it is at any position. So this is my Fp times the Cp value of B. This is Fa times its Cp value, F inert. I can calculate it like that. Or I can calculate Fa naught Cpa plus Fi times Cpi. So this is naught. So I can just consider the inlet values of each, and I am going to assume that, because no assumption necessary, sorry. If this is true, these answers must give you exactly the same value. So whether you choose to decide on updating it with the change in molar flow rates, or whether you use the inlet conditions, if this is true, this will be equal to each other. Who asked that? Was it Dean? Yes, Dean, happy? Everyone happy? Okay, so more questions. I don't know whether Anna is here. She asked about the PBRs or the PFRs in series. More on the PFRs for this question? Nothing? Yes. You only have to worry about it if del CP does not equal 0. Yes. Only have to worry about that if del CP does not equal, and it's not a worry. Worry sounds such a negative word. We only have to make sure that we don't use that one. So worry is not the correct word, but I understand what you mean. Is if del CP is not 0, this will become wrong. This. And you have to consider it there. At each point, you have to update this equation in your function where you are solving for your differential equations. Okay. Right. Okay, so I'm going to stop the recording and start a new one.